Welcome back. In this video we're going to do the solution to the Professor Reese is on a ladder problem. Alright, so we have Professor Reese is at the top of a ladder. That's me right there. Something terrible is going to happen. So this ladder is 10 feet long, and the bottom of it starts to slip away from the house at 1.5 feet per second. At the moment when this distance is 6 feet, how quickly am I dropping? So the idea is that as this ladder drops, Professor Reese at the top of the ladder stays kind of flush with the house and just kind of falls along the edge, right? So the foot of the ladder is coming out, but then the person is kind of staying and just dropping perfectly vertically. All right, so this definitely has a lot more going on in it than the last two examples, so we're going to take our time, we're going to stay confident, and just try some stuff. These problems can definitely be intimidating when you start, but it's all about just kind of diving in. So let's start by labeling the triangle that we clearly have going here, right? So as this ladder falls, the triangle is kind of changing shape, but it's here, right? We have a triangle. So I am going to label all three sides. In general, you can kind of pick whatever letters work best for you. I'll use A, B, and C. So I'll call this side A, this side B, and then that makes this side C. Okay, so if the ladder is 10 feet, I'm going to say that C equals 10. And this is actually a value that we can plug in right away. This is one of those numbers that's safe to plug in. You know, we don't have an equation yet, but when we do, this C really is always 10 because as the ladder falls, it's not going to change, whereas A and B, A gets bigger and B clearly gets smaller. Okay, so we'll say C is 10 always. All right, so the bottom of the ladder slips away at 1.5 feet per second. So that's this right here. So in terms of my picture, I'm going to decide that that's actually dA dt. That is the rate of change of A with respect to time. And you want to take an extra beat here and realize that we did technically just make a decision that dA dt would be positive 1.5. If the ladder was coming towards the house at this same rate, it'd be a subtle difference in the instructions here, but then we would decide that since A is decreasing, dA dt is a negative number, but here because A is increasing, the positive makes sense. Every once in a while, that's kind of a detail that we layer in. Okay, so at the moment when the foot of the ladder is 6 feet, so I'm going to say A is 6, but only just at that second, right? That's like your snapshot value. So this is not something we want to plug in too soon. How fast is Professor Reese falling towards the ground? So what I'm actually solving for here is dB dt. I want dB dt. I want the rate of change of that height. And right now I can expect that my answer will be a negative number because B, this height, is decreasing as I fall. So I'm expecting dB dt to actually be negative. So it'll make sense when that happens at the end. Okay, so you can kind of see these related rates sneaking around. I have dA dt and I want dB dt. That means that I need A and B connected in some sort of equation. I want to connect A and B. Every once in a while there's more than one nice way to do it, but usually the problem is kind of calling for a particular formula. So if you scan your useful formulas sheet, the Pythagorean theorem may be kind of calling out to you, right? We have a right triangle right here. So we know that A squared plus B squared equals C squared. Which is A and which is B in terms of these two sides isn't important here because they just add, but you always want to make sure the hypotenuse is the third side that's alone. All right, so even as the ladder falls, we maintain a right triangle because of the house being presumably vertical. So this should always be true, and it's a formula that has A and B in it, so it should kind of work for our purposes. Okay, so this is the step where we can plug in C equals 10 here. So that's what I'm going to do. I'm sure that that ladder is always 10. So my right-hand side is actually 100. So we're going to do the problem with it like this, and then we'll come back to this step right here, and we'll talk about, well, if you didn't think to plug it in, what would have happened? Would it have gone wrong? And the answer is no. You'd get there pretty quickly. Okay, so moving down, we'll give ourselves some space here. All right, so we have our equation, so now we want to take the derivative with respect to t, right? These are all rates with respect to time, so it's with respect to t in I think every example you'll see in this section. And again, notice, as usual, t is not something here, so everything gets the implicit treatment. So a squared goes to 2a, but then you throw in dA dt. B squared goes to 2b, but we throw in dB dt. And then the derivative of 100 is 0. All right, so that's my derivative step. So now I want to plug stuff in and solve. So what I want is dB dt at this moment, right? So this is the thing that I actually want. So we're not going to plug in there. We want to be able to plug in for everything else. So we're going to need a, dA dt, and a b. All right, so my a will be a equals 6 for that moment data. Once you've taken derivatives, as we have just done, you're free to just plug in everything you've got. You don't have to worry about if it's constant or not. Now it's just fair game. So I'll plug in a 6 for A. For dA dt, we said that was 1.5. But for B, what in the heck? We don't have a value for B, right? This is supposed to be the height of Professor Reese when this is 6. And we don't have that number. So this is one of those moments that I kind of hinted at in the last video. We don't have it, but we have enough information to go find it. So that's what we're going to do. So we say, all right, kind of off to the side here. Let me think about this triangle. This is a particular snapshot moment, right? So that triangle, the hypotenuse is always 10. And at the moment that this side is 6, I want to know what the third side should be. I can solve for that third side, right? A squared plus b squared equals c squared. I'm going to go back to that same formula and use it in a different way. So I know, and I know the 6 and the b look awfully similar. This is a 6, and this is a lowercase b. So I know that b squared plus 6 squared would equal 10 squared. So b squared plus 36 equals 100. 100 minus 36 should be 64, right? Yeah, 64. So b, technically it's the plus or minus square root of 64. Almost ran out of space there. Technically we say plus or minus root of 64, so plus or minus 8. But I'm going to just say positive 8 here because we're talking about a height, right? So clearly it's the positive version. So 8 is what I'm going to plug into that spot right there. And now I have enough to keep going. So 2 times 6 times 1.5 plus 2 times 8 dB dt, that's what we're solving for. So you can simplify these numbers and then solve, or solve and then simplify. I usually just save the calculator step for the end, so I'm going to just kind of leave this as it is. So 2 times 8 dB dt. What I'm doing is subtracting this term onto the right-hand side. So I'll have negative 2 times 6 times 1.5. And then divide both sides by 2 times 8. So dB dt should be negative 2 times 6 times 1.5 over 2 times 8. So if you throw that in a calculator, it comes out to negative 1.125. So this is the rate of change of this distance here, so it's the velocity of the vertical drop. So I'm going to say it's feet per second. But like I said in the previous video, If you don't include units, you won't lose points in this class, but I do encourage you to try to track them as you go. All right, so this is my final answer right here. I want to point out it makes sense that it's negative, and it's also a reasonably sized number. We said we expected that derivative to be negative because b is decreasing as I fall, so its derivative should be negative. All right, so with our last minute here, let's come back to the arrow, right? We said let's come back here and say, well, if I didn't plug in 10, would I have screwed up? And the answer is no, but at some point you have to decide that that ladder isn't changing size. So if you had c squared in this step right here, instead of 0, you would have 2c dc dt. And you'd say, okay, that's 2 times 10 for the ladder times the rate of change of the size of the ladder. And that's the point where you would want to decide that rate of change is 0 because it's a constant length. So you still would have wound up with a 0 in this spot either way. All right, so that's my work, and this is my final answer here.